Okay, now we've been talking about these are particularly exceptions to the octet rule. Now, for the most part, if we can satisfy the octet rule, then we will. And I will not expect you, like if I give you two elements and ask you to come up with the molecular formula, I will not expect you to figure out that somehow the octet rule is being broken for you to come up with that compound. However, if I do give you a compound with a specific molecular formula and I ask you to draw the Lewis structure of it, you may have to show that it's violated the octet rule in some way. So one of the ways that the octet rule may be violated is if we have an odd number of electrons around one atom, and that odd number tends to be less than 8. So a very well-known example is NO, which is also known as, let me get the name here, as nitric oxide. And this is actually a very important compound in cellular signaling. So if I have nitrogen, it's like this. So once I've drawn my structure, I could either have this or I could have this. And both structures, neither of them satisfies the octet rule, so neither is very happy. But if I count the number of valence electrons, remember that nitrogen has to have 5, oxygen contributes 6 to this whole bonding. So it's not that you are going to figure this out on your own so much as I will say this is N, and I'll give you have the compound NO, and you will have to draw one of these structures, perhaps. Another exception is if we are talking about we get less than an octet. So sometimes you have elements like beryllium and boron. Beryllium has 2 valence electrons, boron has 3 valence electrons. So normally we might assume that these two will actually lose their valence electrons like metals will. However, beryllium and boron actually probably behave a little more like metalloids, where they're a bit ambivalent as to whether they want to lose or gain electrons. Part of this is because, the having less than 4, normally you would expect them to have low ionization energies. However, they have a fairly high effective nuclear charge with a relatively small radius, so they still have some pull on their electrons. So what may happen is instead that they will hybridize. So if the electrons will jump into different orbitals, so if I take Be, what may happen is this 1s, or these 2s electrons, one of them may jump into a p orbital. So what happens is you get a Lewis structure that looks like this. And if you look at that, then you could say, oh, well, this electron and this electron now can pair up with electrons of another element. Boron does a similar thing, so it will end up hybridizing so that you can see that it could form 3 bonds. So if we look at boron trifluoride, notice how that single electron will pair up there. This single electron will pair up here, and this one will pair up with one from another fluorine. I'm getting quite messy, sorry. So we end up with BF3. And it's sort of like this odd sort of empty orbital is hanging around out here. So what also can happen, there are other things that might happen to make that a little more stable. What can happen too is if we've got B and F, is that, so say this fluorine has its 6 unpaired electrons. What it may do is it may donate one of those pairs of unbonded electrons to boron, so then it forms a double bond. And in that way, the octet rule is satisfied. And then if we think of resonance, well, that double bond could be here, it could be here, or it could be here. The other possibility is that this weird empty orbital is still hanging out there. The octet rule isn't satisfied. And then something like ammonia comes along. So ammonia, if we look at nitrogen, which has 2 valence electrons on top here and single valence electrons here, well, these 2 electrons don't get involved in bonding. So what may happen is if ammonia comes along, sees boron trifluoride, what may happen is that boron will donate its 2 electrons and will form a bond between itself and boron. So then in this way now, boron's satisfied with an octet, ammonia is still satisfied with an octet. So the last exception is when we get something that is more than an octet rule. This only happens with elements in the 3rd period or below. The reason why is that electrons have to hybridize into d orbitals. So if we look at our principal energy levels and what subshells are in those energy levels, we have 1s, we have 2s and 2p, we have 3s, p, and d. So once we get to the 3rd energy level, then electrons can start jumping into maybe this d subshell, so that more electrons are single and can pair up with the electrons of other elements. This also only tends to happen when elements run into crazy, highly electronegative elements like chlorine and fluorine. So if we look at phosphorus, for instance, phosphorus normally has 5 valence electrons. If we look at our orbitals, that's distributed like this. 3s has 2, and 3p has 3, 1 in each shell. So then when things bond up, that means that we can bond with 3 other things here. So we could have plain old phosphorus trifluoride, however, what may also happen is that 3s electron, one of the 3s electrons, could jump into a d orbital. And remember that d's have 5 possible orbitals. So if we take one of our 3s electrons and we jump it over, we end up with this. And now we see that there are 1, 2, 3, 4, 5 unpaired electrons. So now that phosphorus could bond with 5 different fluorines, so that we end up with a bond that looks like this. And so this is when we have an expanded octet, sometimes is what we refer to it as. So that is it for this section.